when did people start thinking of regression like in terms of loss minimization? So regression has, least squares regression is from like the early 1800s. So it's been around for, kind of, you could call it the first machine learning that was ever done, if you want. I guess the loss minimization framework is, it's hard to kind of pinpoint a particular point in time. It's kind of not a terribly, it's not like a, innovation in some sense. It's just more of a, at least right now, it's kind of a pedagogical tool to organize all the different methods that exist. Yeah.
Say I'm training on median. Do you mean that like in that particular training set, the median would be the highest accuracy, most confident, whereas like with loss absolute deviation would be the median instead of the mean?
Yeah. So I didn't want to get into this example, but briefly, if you have 3 points that you can't exactly fit perfectly, if you use absolute deviation, then you're going to find the median value. You're going to basically predict the median value. And if you use the square loss, you're going to predict the mean value. But I'm happy to talk offline if you want. OK, so what we've talked about so far is we have these wonderful linear predictors, which are driven by feature vectors and wave vectors. And now we can define a bunch of different loss functions that capture how we care about regression and classification. And now let's try to actually do some real machine learning. How do you actually optimize these objectives? So remember, the learner is going, so now we talked about the optimization problem, which is minimizing the training loss. We'll come back to that next lecture. And then now we're going to talk about optimization algorithm. OK? So what is the optimization problem? Now, remember last time we said, OK, let's just abstract away from the details a little bit. Let's not worry about if it's the square loss or some other loss. Let's just think about it as a kind of abstract function. So in one dimension, the training loss might look something like this. You have a single weight, and for each weight, you have a number which is your loss on your training examples. Okay? And you want to find this point. So in 2 dimensions, it looks something like this. And let me try to actually draw this, because I think it will be useful in a bit. So let me pull this up. OK, so in 2 dimensions, what optimization looks like is as follows. So I'm now plotting W1 and W2, which are the 2 components of this 2-dimensional wave vector. For every point, I have a wave vector, and that value is going to be the loss, the training loss. And it's pretty standard in these settings to draw what are called level curves. So let's do this. So each curve here is a ring of points where the function value is identical. So if you look at terrain maps, those are level curves, so kind of what I'm talking about. So this is the minimum, and as you kind of grow out, you get larger and larger. OK, I'll keep on doing this for a little bit. OK. All right. And the goal is to find the minimum. OK. All right, so how are we going to do this? So, yeah, question?
Assuming that there is a single minimum.
Yeah, why am I assuming there is a single minimum? In general, for arbitrary loss functions, there's no necessarily a single minimum. I'm just doing this for simplicity. It turns out to be true for many of these linear classifiers. OK, so last time we talked about gradient descent, right? And the idea behind gradient descent is that, well, I don't know where this is, so let's just start at 0, as good as any place. And what I'm going to do at 0 is I'm going to compute the gradient. So the gradient is this vector that's perpendicular to the level curves. So the gradient is going to point in this direction. That says, hey, in this direction is where the function is increasing the most dramatically. And gradient descent says goes in the opposite direction. right? Because remember, we want to minimize loss. So I'm going to go here. And now I'm hopefully reduced my function value. Not necessarily, but we hope that's the case. Now we compute the gradient again. The gradient says, maybe it's pointing this way. So I go in that direction. And maybe now it's pointing this way. And I keep on going. This is a little bit made up. But hopefully eventually I get to the origin. And I'm kind of simplifying things quite a bit here. So there's a whole field of optimization that studies exactly what kind of functions you can optimize and how gradient descent, when it works and when it doesn't. I'm just going to kind of go through the mechanics now and defer the kind of the formal proofs of when this actually works until later. Okay, so that's kind of the schema of how gradient descent works. So in code, this looks like this. So initialize at 0, and then loop on some number of iterations, which let's, for simplicity, just think there's a fixed number of iterations. And then I'm going to pick up my weights, compute the gradient, move in the opposite direction, and then there's going to be a step size that tells me how fast I want to make progress. Okay, and we'll come back to what the step size does later. Okay, so let's specialize it to least squares regression. So we kind of did this last week, but just to kind of review. So the training loss for least squares regression is this. So remember, it's an average over the loss of individual examples, and the loss of a particular example is the residual squared. So that's this expression. And then all we have to do is compute the gradient. And if you remember your calculus, it's just use the chain rule. So this 2 comes down here. You have the the residual times the derivative of what's inside here, and the gradient with respect to w is phi of x. Okay. So last time we did this in Python in 1 dimension. So in 1 dimension, hopefully all of you should feel comfortable doing this because this is just kind of basic calculus. Here we have w is a vector. So we're not taking derivatives, but we're taking gradients. So there's some things to be wary of. But in this case, it's often kind of useful to double check that, the gradient version actually matches the single dimensional version as well. Because last time, remember, we have x out here. And one thing to note here is that there's the prediction minus target. That's the residual. So the gradient is driven by kind of this quantity. So if the prediction equals the target, what's the gradient? It's going to be 0, which is kind of what you want. If you're already getting the answer correct, then you shouldn't want to move your weights, right? So often, we can do things in the abstract and everything will work. But it's often a good idea to write down some objective functions, take the gradient, and see if gradient descent on using these gradients that you computed is kind of a sensible thing, because there's kind of many layers you can understand and get intuition for this stuff at the kind of the abstract level optimization or kind of at the algorithmic level. Like you pick up an example, is it sensible to update when the gradient or then when the prediction equals the target? Okay, so let's take the code that we have from last time, and I'm going to expand on it a little bit and hopefully set the stage for doing stochastic gradient. Okay, so last time we had gradient descent. Okay, so remember last time we defined a set of points. We defined the function, which is the train loss here. We defined the derivative of the function, and then we had gradient descent. Okay, so I'm going to do a little bit of house cleaning. Don't mind me. Okay, so I'm going to make this a little bit more explicit what this algorithm is. Gradient descent depends on a function, a derivative function, and let's say the dimensionality. And I can call this gradient with f, df, and in this case it's d, where d equals 2. Okay, and I want to kind of separate. This is the kind of algorithms, and this is modeling. So this is what we want to compute, and this is how we compute it. Okay, and this code should still work. Okay. All right, so what I'm going to do now is upgrade this to vectors. So remember, the x here is just a number, right? But we want to support vectors. So in Python, I'm going to import numpy, so which is this nice vector and matrix library. And I'm going to make some arrays here. And this is just going to be a one-dimensional array, so it's not that exciting. So this w.x becomes the actual dot I need to call, and I think, and w it needs to be mp.zeros d. Okay. All right, so that should still run. Actually, sorry, this is one-dimensional. Okay, so remember last time we ran this this program, and it starts out with some weights, and then it converges to 0.8, and the function value kind of keeps on going down. Okay. All right, so let's try to it's really hard to kind of see whether this algorithm is doing anything interesting because we only have 2 points. It's kind of trivial. So how do we go about because I'm going to also implement stochastic gradients, and how do we have kind of a test case to see if this algorithm is working? So there's kind of this technique which I really like, and it's which is to call generate artificial data. And the idea is that what is learning? You're learning as you're taking a data set and you're trying to find the weights that best fit that data set. But in general, if I generate if I download a data set, I have no idea what the right kind of quote unquote right answer is. So there's a technique where I go backwards. I say, okay, let's decide what the right answer is. So let's say the right answer is 1, 2, 3, 4, 5. So it's a 5-dimensional problem. Okay. And I'm going to generate some data based on that, so that this weight vector is kind of good for that data. Oops. I'm going to skip all my breaks in this lecture. So I'm going to generate a bunch of points. So let's generate 10,000 points. The nice thing about artificial data is you can generate as much as you want. There's a question, yeah?
A true W?
Oh, so true W just means like the ground truth W. Is this
like true Y, like the true output? Or?
So W is a weight vector. So this is kind of going backwards. Remember, I want to fit the weight vector, but I'm just kind of saying this is the right answer. So I want to make sure that the algorithm actually recovers this later. Okay, so I'm going to generate some random data. So there's a nice function, random.randn, which generates a random d-dimensional vector. And y, I'm going to set, what should I set y to?
Which side of W is on?
Yeah, so I'm going to do regression. So I want to do true W dot x, right? So, I mean, if you think about it, if I took this data and I found like true W is the right thing, that will get 0 loss here, okay? But I'm going to make life a little bit more interesting. I'm going to add some noise. Okay. So let's print out what that looks like. Also, I should add it to my data set. So Python gradient. Okay, so this is my data set. Okay, I mean, can't really tell what's going on, but you can look at the code and you can assure yourself that this data has structure in it. Okay, so let's get rid of this print statement and let's train and see what happens. So okay. Oh, one thing I forgot to do. So if you notice that the objective functions that I've written down, they have a divided by the number of data points. I want the average loss, not the sum. It turns out that if you have the sum, then things get really big and blow up. So let me just normalize that. Okay, so let me not get rid of that. Okay, so it's training. It's training. Actually, so let me do more iterations. So I did 100 iterations. Let's do 1,000 iterations. Okay. So the function value is going down. That's always something good to check. And you can see the weights are kind of slowly getting to what appears to be 1, 2, 3, 4, 5, right? Okay. So this is not hard proof, but it's kind of evidence that this learning algorithm is actually kind of doing the right thing. Okay, so now let's see if I add more points. So I now have 100,000 points. Now obviously it gets slower, and it'll hopefully get there one day. But I'm just gonna kill it. Okay, any questions about? Oops, my terminal got screwed up. Okay, so what I do here? I define loss functions, took their derivatives. The gradient descent is what we implemented last time, and the only thing different I did this time is generate a data set so I can kind of check whether gradient descent is working. Yeah, question?
So the fact that the gradient is just a residual, like this residual squared, is that what enables the algorithm to learn from over predictions versus under predictions?
The question is whether the fact that the gradient is residual allows the algorithm to learn from under or over predictions. Yeah, so the gradient is, if you think about it, yeah, that's good intuition. So if you look at, if you're over predicting, right, that means the gradient is kind of, assume that this is like 1. So that means this is going to be positive, which means that, hey, if you up that weight, you're going to over predict more and more and incur more loss. So by subtracting the gradient, you're kind of pushing the weights down in the other direction. And same for when you're under predicting. Yeah, so that's good intuition to have. Yeah?
Of the noise when you generate y plus ws.
What is the effect of the noise? The effect of noise, it makes the problem a little bit harder, so that it takes more examples to learn. If you shut off the noise, then it will, we can try it. I have never done this before, but presumably you'll learn faster, but maybe not. The noise isn't that much, but okay. So let's say I have like 1,000 examples. That's quite a few examples, and now this algorithm runs pretty slowly, right? And in modern machine learning, you have millions and hundreds of millions of examples. So gradient descent is going to be pretty slow. So how can we speed things up a little bit? And what's the problem here? Well, if you look at what the algorithm is doing, it's iterating, and each iteration it's computing the gradient of the training loss. And the training loss is just average of all the points, which means that you have to go through all the points, and you compute the gradient of the loss, and you add everything up. And that's what is expensive and takes time. So, you might wonder, well, how can you avoid this? I mean, if you want to do gradient descent, you have to go through all your points. And the key insight behind stochastic gradient descent is that, well, maybe you don't have to do that. So maybe, here's some intuition, right? So what is this gradient? So this gradient is actually the sum of all the gradients from all the examples in your training set, right? So we have 500,000 points adding to that. So actually what this gradient is it's actually kind of a sum of different things which are maybe pointing in slightly different directions, which all average out to this direction, okay? So maybe you can actually not average all of them, but you can average just a couple, or maybe even in an extreme case, you can just like take one of them and just march in that direction. So here's the idea behind stochastic gradient descent. So instead of doing gradient descent, we're going to change the algorithm to say for each example in the training set, I'm just going to pick it up and just update. It's instead of like sitting down and going over all the training examples and thinking really hard, I'm just going to pick up one training example and update right away. So kind of the key idea here is it's not about quality, it's about quantity. Maybe not the world's best life lesson, but it seems to work in here. And then there's also this question of what should the step size be. And generally in stochastic gradient descent, it's actually even a bit more important because when you're updating on each individual example, you're getting kind of noisy estimates of the actual gradient. And people often ask me like, oh, how should I set my step size? And the answer is like, there is no formula. I mean, there are formulas, but there's no kind of definitive answer. Here's some general guidance. So if step size is small, so you're really close to 0, that means you're taking tiny steps, right? That means that it'll take longer to get where you want to go, but you're kind of proceeding cautiously, so it's less likely you're going to, if you mess up and go in the wrong direction, you're not going to go too far in the wrong direction. Conversely, if you have A to be really, really large, then it's like a race car. You kind of drive really fast, but you might just kind of bounce around a lot. So pictorially, what kind of this looks like is that here's maybe a moderate step size, but if you're taking steps, really big steps, you might go over here and then you jump around, and then maybe you end up in the right place, but maybe sometimes you can actually get flung off out of orbit and diverge to infinity, which is a bad situation. So there's many ways to set the step size. You can set it to a constant. You could usually have to tune it, or you can set it to be decreasing. The intuition being that as you optimize and get closer to the optimum, you kind of want to slow down, right? Like if you're coming on the freeway, you're driving really fast, but once you get to your house, you probably don't want to be like driving 60 miles an hour. Okay, so actually I didn't implement stochastic gradient, so let me do that. So let's try to get stochastic gradient up and going here. Okay, so the interface to stochastic gradient changes. So in gradient descent, all I need is a function, and it just kind of computes the sum over all the training examples. So in stochastic gradient, I'm going to just note SF for stochastic gradient. I'm going to take an index I, and I'm going to update on the ith point only. So I'm going to only compute the loss on the ith point. And same for its derivative. I'm going to look at the ith point and just compute the gradient on that ith point. Okay? And this should be called SDF. Okay, so now instead of doing gradient descent, let's do stochastic gradient descent. And I'm going to pass in SF, SDF, D, and the number of points, because I need to know how many points there are now. Copy gradient descent, and it's basically kind of the same function. I'm just going to stick another for loop in there. So stochastic gradient descent, it's going to take the stochastic function, the stochastic gradient, the dimensionality, and n. Okay, so now before I was just going through number of iterations, and now, right, I'm not going to try to compute the value over all the training examples. I'm going to loop over all the points, and I'm going to just evaluate the function at that point I, and compute the gradient at that point I instead of the entire data set. And then everything else is the same. I mean, one other thing I'll do here is that I'll use a different step size schedule. So 1 divided by number of updates. So I want it so that the number of the step sizes kind of decrease over time. Okay, so I start with 8 equals 1, and then it's half, and then it's a third, and it's a fourth, and it keeps on going down. Sometimes you can put a square root, and that's more typical in some cases, but I'm not going to worry about the details too much. Question?
The point I is chosen randomly, but here we just do it for every range.
Yeah, so the question is, the word stochastic means that there should be some randomness here. And technically speaking, the stochastic gradient descent is where you're sampling a random point and then you're updating on it. I'm cheating a little bit because I'm iterating over all the points. In practice, if you have a lot of points and you randomize the order, it kind of is similar, but there is a kind of a technical difference that I'm trying to hide. Okay, so this is stochastic gradient descent. Loop, iterate, go over all the points and just update. Okay, so let's see if this works. Okay. I don't think that worked. Maybe, let's see what happened here. I did try it on 100,000 points. Maybe that works. Oh, nope, that didn't work either. Anyone see the problem? Oh, so I'm printing this out at the end of each iteration, so that should be fine. Really, this should work. So gradient descent was working, right? Maybe I'll try. It's probably not the best idea to be debugging this live, but okay, let's make sure gradient descent works. Okay, so that was working, right? Okay, so stochastic gradient descent. I mean, it's really fast and converges, but it doesn't converge to the right answer. Yeah, but that should get incremented to 1. So that it might be true. Okay, so I do have a version of this code that does work. So what am I doing here that's different? Okay, have some water. Maybe I need some water. Okay. So this version works. Yeah. Yeah, that's probably good. That's a good call. Yeah. Okay. All right, now it works. Thank you. So yeah, this is a good lesson. Is that when you're dividing, this needs to be 1. Actually, in Python 3, this is not a problem, but I'm still on Python 2 for some reason. But this should be a 1.0 divided by num updates. Otherwise, I was getting.
So how is it faster?
Okay, so why is it faster? Yeah. Okay. Okay. Let's go back to 500,000. Okay. Okay. So one full sweep over the data is the same amount of time, but you notice that immediately it already converges to 1, 2, 3, 4, 5. Right. So this is like way faster than gradient descent. Remember, just to kind of compare, gradient descent is you run it, and after one step, it's like not even close. Right? Yeah. What noise levels do you have to have until gradient descent becomes better? So it is true that if you have more noise, then gradient descent might be stochastic gradient descent can be unstable. There might be ways to mitigate that with step size choices, but yeah, probably you have to add a lot of noise for stochastic gradient to be really bad. I mean, this is in some sense, if you take a step back and think about what's going on in this problem, it's a 5-dimensional problem. There's only 5 numbers, and I'm feeding it 500,000 data points, right? There's not that much to learn here, and so there's a lot of redundancy in the data set. And generally, actually, this is true. Like in a large data set, there's going to be a lot of redundancy. So going through all the data and then trying to make an informed decision is pretty wasteful, where sometimes you can just kind of get a representative sample from one example, or more is common to do like kind of mini batches where you maybe grab 100 examples and you update on that, so there's a way to be somewhere between stochastic gradient and gradient descent. Okay, let me move on. Okay, summary so far, we have linear predictors, which are based on scores. So linear predictors include both classifiers and regressors. We can do loss minimization, and we can, if we implement it correctly, we can do SGD. Okay, so I'm kind of switching things. I hope you're kind of following along. I introduced binary classification, and then I did all the optimization for linear regression. So now let's go back to classification and see if we could do stochastic gradient descent here. Okay, so for classification, remember we decided that the 0-1 loss is the thing we want. We want to minimize the number of mistakes. Who can argue with that? So remember, what does 0-1 loss look like? It looks like this. Okay, so what happens if I try to run stochastic gradient descent on this? I mean, I can run the code, but yeah, it won't work, right? And why won't it work? Yeah, so two popular answers are it's not differentiable. It's one problem. But I think that the bigger problem, kind of the deeper problem, is that what is the gradient? Zero. It's like zero basically everywhere except for this point, which doesn't really matter. So as we learned, that if you try to update with a gradient of 0, then you won't move your weights, right? So the gradient descent will not work on the 0-1 loss. So that's kind of unfortunate. So how should we fix this problem? Yeah. Yeah, let's make the gradient not 0. Let's skew things. So there's one loss, which I'm going to introduce, called the hinge loss, which does exactly that. So let me write the hinge loss down. And the hinge loss is basically is 0 here when the margin is greater or equal to 1, and rises linearly. So if you've gotten it correct by a margin of 1, so you're kind of pretty safely on the side of I'm getting it correct, then we won't charge you anything. But as soon as you start dipping into this area, we're going to charge you kind of a linear amount, and your loss is going to grow linearly. So there's some reasons why this is a good idea. So it upper bounds the 0-1 loss. It has a property known as convexity, which means that if you actually run the gradient descent, you're actually going to converge to the global optimum. I'm not going to get into that. And so that's a hinge loss. So what remains to be done is to compute the gradient of this hinge loss. Okay. So how do you compute this gradient? So in some sense, it's a trick question because the gradient doesn't exist because it's not differentiable everywhere. But we're going to pretend that little point doesn't exist. Okay. So what is this hinge loss? The hinge loss is actually two functions, right? There's a 0 function here, and then there's like this 1 minus x function. So what am I plotting here? I'm plotting the margin and the loss. Okay. So this is the 0 function, and this is 1 minus w dot phi of xy. And the hinge loss is just the maximum of these two functions. So at every point, I'm just taking the top function. So that's how I'm able to trace out this curve. Okay. All right. So if I want to take the gradient of this function, you can try to do the math, but let's think through it. what should the gradient be? Well, if we're here, what should the gradient be? It's 0. And if I'm here, what should the gradient be? It should be whatever the gradient of this function is, right? So in general, when you have a gradient of this kind of max, you have to kind of break it up into cases, and depending on where you are, you have a different case. So loss is equal to, if I'm over here, and what's the condition for being over here? If the margin is greater than 1, right? And then otherwise, I'm going to take the gradient of this with respect to w, which is going to be minus phi of xy, otherwise. Okay. So again, we can try to interpret the gradient of the hinge loss. So remember, you're doing stochastic gradient descent. You have a wave vector, and you're going to pick up an example, and you say, oh, let's compute the gradient, move away from it. So if you're getting an example right, then the gradient is 0. Don't move, which is the right thing to do. And otherwise, you're going to move in the direction, because you're minus minus, of phi of xy, which kind of imprints this example into your weight vector. So, and you can formally show that it actually increases your margin after you do this. Okay? Yeah?
The margin 1.
What's the significance of the margin being 1? This is a little bit arbitrary. You're just kind of setting a non-zero value. And in support vector machines, you set it to 1, and then you have regularization on the weights, and that gives you some interpretation. So I don't have time to go over that right now, but feel free to ask me later. There's another loss function. Do you have a question?
Yeah. Why do we choose the margin as the loss function as opposed to like the squared error or another?
Yeah. So why do you choose the margin? So in classification, we're going to look at the margin because that tells you how confidently you're predicting correctly. In regression, you're going to look at residuals and square losses. So it depends on kind of what problem you're trying to solve. Just really quickly, some of you might have heard of logistic regression. Logistic regression is this yellow loss function, right? So the point of this is saying that this loss minimization framework is really general, and a lot of things that you might have heard of, least squares, logistic regression, are kind of special cases of this. So if you kind of master how to do loss minimization, you kind of can do it all. Okay, so summary. Basically what's on the board here. If you're doing classification, you take the score, which comes from w dot phi of x, and you drive it into the sign, and then you get either +1 or -1. Regression, you just use the score. Now to train, you have to assess how well you're doing. In classification, there's the notion of a margin. In regression, it's the residual. And then you can define loss functions. And we only talked about 5 loss functions, but there's many others, especially for a kind of structure prediction or ranking problems. There's all sorts of different loss functions. But they're kind of based on these simple ideas of, you have a hinge that upper bounds to 0, 1 if you're doing classification, and some sort of square-like error for regression. And then once you have your loss functions, provided it's not 0, 1, you can optimize it using SGD, which turns out to be a lot faster than gradient descent. Okay, so next time we're going to talk about phi of x, which we've kind of left as someone just hands it to you. And then we're also going to talk about what is the really true objective of machine learning? Is it really to optimize the training loss? Okay, until next time.